Hello everyone, welcome back to my Chem Corner. So in today's video we're going to talk about packing efficiency from first chapter in solid state. So before we move into the video, please remember to subscribe to the channel and hit the bell icon so you get notifications whenever I upload the video. So let's move into this. Now packing efficiency, we're basically looking at the percentage of total space that is occupied by particles in a crystal, and that's called as packing efficiency. So we saw this the same thing in closed pack structures when we looked at 1 dimension, 2 dimension and 3 dimension. We saw the efficiency of these particles being closely packed in it. Now we will look at the percentage in each type of a unit cell. Now that is a fraction of total space occupied by the particle is called as a packing fraction. Now we will be looking at packing efficiency in cubic closed packing. We will look at body-centered cubic structures and in face-centered cubic structures. So we will be moving in detail. We will be calculating the percentage of packing efficiency in each of this. So the first one is packing efficiency in a CCP or a HCP. The full form of CCP is cubic closed packing and HCP is hexagonal closed packing. Now when you look at the structure here, naming of each of these lattice points and what these small a and small b are is important. So here the small a is nothing but the edge length and the small b is the hypotenuse. So we're going to use these terms and we're going to calculate the packing efficiency for CCP and HCP. So now we're going to look at basic mathematics. We're going to take triangle ABC. So we have triangle ABC. So this is the particular triangle that we're looking at. Now in that we're going to look at Pythagoras theorem. So we have the square of the hypotenuse, which is equal to square of other two sides, sum of squares of other two sides. So here we have AC square, which is the hypotenuse, and which is equal to AB square plus BC square, which is the other two sides. Now here AC square is nothing but B square we can write, and AB square and BC square is nothing but A square. Those are the terms given. So we'll just write that here. Now a square plus a square can be written as 2a square after simplification. Because we need only the value of b, we will write root of 2a. So that is the value of b that we have got. Now if the radius of the sphere is r, so we have these atoms here, these spheres. If the radius of these spheres are considered as r, in that case we will have b is equal to 4r, because if you look at b, the line b, which is the hypotenuse, you have 3 spheres. Out of these 3 spheres, the first sphere, half circle is on this hypotenuse. So we have 1 radius over here. The center sphere has 2 radius, both of it are on the hypotenuse, and the last sphere, which is here, the half of the circle is on the hypotenuse. So totally we have 4r or 4 radius. So I've just written that 4r, which is further equal to root of 2a. Now when we further simplify that, a is equal to 4r by root 2. When you simplify this, you will get 2 root 2r. Now this is going to be the value of a. So let's keep that calculation aside. Now if you look at the unit cell of this CCP, these will have 4 spheres. Alright, so when it has 4 spheres, the volume of one sphere is going to be 4 by 3 pi r cube. Now this is the formula of a sphere, volume of a sphere. Now because in a closed CCP, each unit cell has got 4 spheres, therefore we are going to write volume of all 4 spheres is equal to 4 into 4 by 3 pi r cube. Simple calculation. Now because we're learning about a cube, volume of a cube is also prime importance. So here volume of cube is nothing but a cube. We just calculated what the value of a is, which is 2 root 2r cube. So we put that also. So now we know what is the volume of cube. We know what is the volume of all four spheres. We are going to write the formula of packing efficiency. So here in common, the packing efficiency is equal to volume occupied by the spheres in a unit cell divided by total volume of unit cell into 100. So this is going to be the common formula. What varies is depending on what type of a unit cell you're studying, whether it is 4 sphere, 1 sphere or 2 sphere, this is going to change. So here when we substitute the values, volume of 4 spheres is 4 into 4 by 3 pi r cube. We just wrote it here. Divided by total volume of the unit cell is here 2 root 2 r the whole cube into 100. When we simplify this is equal to 74%. So the percentage of packing efficiency in a CCP or a HCP is going to be 74%, the highest basically when comparing the other two. Now, if asked whether you're supposed to calculate this using a calculator in your exam, not needed, because this is not going to change. It is going to remain standard. So you just have to write that 74% directly. You don't have to show calculation for this part here. But writing the formula, the substitution and final answer is important. Now let's move to the next one, which is packing efficiency in a BCC. Now when you look at packing efficiency in a BCC, you need to remember a BCC unit cell. So here if you see, this is across the unit cell. So this is like when you're sitting in a room and the center of the room you have a sphere hanging from the fan probably. So that is the sphere C in the center, right? So it is across the unit cell. Now here we are going to look at triangle EFD. So the calculation is almost similar to the previous one, but probably there would be an addition because you have an extra sphere placed probably in the center of the unit cell or probably in the face centers. So then you will have difference in the calculation of using the Pythagoras theorem, but the remaining part of the calculation almost remains the same. So here in this particular triangle, if you see EFD, the one that is at the bottom, that particular triangle, if you're seeing, you're going to apply again the Pythagoras theorem itself. So here if you see, your hypotenuse is this FD. So FD square is equal to ED square plus EF square. EF square plus DE square. So here same thing, we have given the edges as A and the hypotenuse as B. That remains standard. So we'll just substitute the values. FD square is given as B here and the edge length is given as A. When we substitute it, it's going to be the same value that you get as you got in the CCP or HCP. B is equal to root 2A. Now that's not the only thing in a BCC because we have a sphere right in the center of the unit cell. So we need to consider that particular triangle also. So let's see the second triangle, which is AFD, which involves the body centered atom also. So here when we look at AFD, in this case, the hypotenuse is AF. Now because it has the body centered sphere, we are naming that particular hypotenuse just to give a difference between this hypotenuse and the previous hypotenuse. That is named as C. So when we write down, we will write FA square is equal to AD square plus FD square. So FD is already named as B, which is the hypotenuse of the previous triangle. This AD is the normal edge length of any cube. AF is the new hypotenuse which contains the body centered atom. Now we'll just substitute the values into it. So FA is nothing but C, AD is A and FD is going to be B. So when you put that, you will get an equation like this. Now every term here is different. You don't have further calculation, but there is one where you can make it simple. We have just calculated what is B, which is root of 2A. So instead of having A, we can just put, instead of having B, we can just substitute instead of B this entire value. So when we do that, we will get C square is equal to A square plus 2A square. When we put the value here, the root will get cancelled. You get 2A square. 2a square plus a square is equal to 3a square. So here when we write c value, this will become root of 3a. So we have the value of b, we have the value of c also. Now the remaining part of it remains the same, just like how we did for CCP and HCP. So here, if the radius of the sphere is given as r, in that case, again on this particular hypotenuse, you have 4 radius. 1 radius from this sphere, 2 radius from the center sphere, and 1 radius from here. So total we have 4 radius. So therefore, C is equal to 4r. On C we have 4 radius, which is equal to root of 3a. Now when we simplify that, you will get a is equal to 4r by root 3, because we need the value for edge length. So a is equal to 4r by root 3. Now we'll keep this aside. We will be using this directly into the calculation. Now we will see for a BCC how many atoms are belonging to it, which we did a calculation on in the previous videos. So here in each unit cell in a BCC has 2 spheres to itself. We did this calculation in the previous videos also. If you haven't watched that, I'll put the link in the description box and you all can watch how to calculate that, how many atoms belong to a particular unit cell. So here for a BCC, 2 spheres belong to itself. Now the volume of a sphere general formula is 4 by 3 pi r cube. So because each BCC has 2 spheres belonging to itself, so volume of those 2 spheres is equal to 2 into 4 by 3 pi r cube. Next is the volume of the cube. General formula is a cube. A cube is nothing but this we just calculated here, 4r by root 3, the whole cube. So now we have the volume of the cube, we have the volume of 2 spheres. We can directly calculate the packing efficiency in BCC using the formula volume occupied by 2 spheres in a unit cell divided by total volume of unit cell into 100. So if you see the formula, the only difference between HCP packing efficiency formula and BCC packing efficiency formula is this value here. For HCP and CCP, which is generally observed in a face-centered cube, it was 4 spheres. In this case, because it's a BCC, it is 2 spheres. So now we'll just substitute the value. The volume occupied by 2 spheres we just calculated here, 2 into 4 by 3 pi r cube divided by total volume of unit cell, which is 4r root 3 the cube, which is, when we calculate this, you will get 68%. So here this is going to be the percentage for a BCC, 68%. Now let's move on to the last packing efficiency, which is a simple cube. This is much more easier because it's a very simplified version of whatever we learned right now, because we don't have a face-centered sphere, we don't have a body-centered sphere. This is just going to be a simple cube. So here I have a diagram for it. So we just have a simple cube. We're just looking at these 2 spheres which are there at the edge. There's nothing as such as a hypotenuse because we don't have any sphere in a simple cube which is coming on the face center or at the body center. So the calculation of the hypotenuse or the calculation using the Pythagoras theorem is not there in this case. So here we will see that in a simple cubic lattice, the particles are located at the corner. That's all. It's a very simple thing. So we will move directly into this. In this, the edge length is named as A and it's named A throughout the entire packing efficiency that we learned. In this case, the radius is also named as R. So on one particular edge, if you see how many radius is there, from this sphere we have 1 radius, from this sphere we have 1 radius completing an entire edge length. So in this case, A is equal to 2R. We have only 2 radius. Now, when you calculated number of atoms per unit cell for a simple cube, we calculated there was only 1 sphere that actually belonged to itself. So here each unit cell in a simple cubic structure has only 1 sphere. Therefore, volume of that 1 sphere is going to be 1 into 4 by 3 pi r cube. Very simple one. Similarly, the volume of the cube A cube is equal to 2r the whole cube. We have the volume of the cube, we have the volume of the sphere. write down the formula for packing efficiency, which is volume occupied by one sphere divided by total volume into 100. So volume occupied by one sphere is here and the total volume is here. 2r the whole cube into 100 substituted. When we calculate, you will get 52.4%. So if you see, the packing efficiency percentage is higher in a HCP or a CCP, which is found in a face-centered cube. And below that we have the BCC, and the least one is going to be for a simple cube. So here only the three types are there. These packing efficiency is very important because in a PUC board exam paper, one packing efficiency problem for either 3 mark or 4 mark is there in the paper. It's a compulsory question. So please don't skip this part. Please watch the entire video, and if you have any sort of suggestions, please don't forget to put it down in the comment box, or you can write an email in the email ID mentioned in the description box. I'll see you in the next video. Stay tuned for another video. Thank you.